Hi, my name is Leon Starr, and welcome to video 4 in the road subsystem modeling series. In this video, we'll model the types and composition of lanes within a road segment. Here is a busy road segment approaching an intersection. Using what you know from the previous videos, you should be able to identify two roads in this picture. Let's call them R1 and R2. And you can also make out three distinct road segments on each side of the intersection. RS1 through 4, let's say. We'll focus on RS1 in the foreground, and here we see a forward and a reverse conduit. But there's still quite a lot going on that we haven't discussed yet. In the next two videos, we will be focusing on how the various types of lanes are defined. But let's start with the less complex scene, and then we'll come back to this one later in the video. Here we'll take a look at the lanes and the forward conduit of road segment RS1 in the foreground. If we want our model to work universally in regions where you drive on the right, such as the USA, or on the left, such as Japan or the UK, we need to stop using the terms left and right. Left and right works okay if we talk about a road segment having left and right edges, as we do in our model, since that fact doesn't change in any country. And we can still use the terms when we talk about turning on the left and right signals when driving. But when it comes to internal road structures, we're going to need something more universal. We propose using the terms inside and outside instead. On a two-way road, inside will be toward the median and outside will be toward the sidewalk. Of course, you might not have a median or a sidewalk, but it's the same principle. So in the USA, outside is to the right and inside is to the left. It's the other way around in Japan. This next scene will help us get started incorporating simple lanes into our model. We can easily see that the forward traffic flow is separated by a set of parallel lane divisions. We'll use numbers to name them in no particular order. And we'll model this concept of a lane division with a class in the upper right. To avoid getting lost in abstraction, we populate our new lane division class with a simple table. Looking at any given lane division, we see that it may be on the inside, toward the median, relative to an adjacent division on the outside, toward the shoulder. LD1 is inside relative to LD5 on the outside, for example. We're going to define a lane as the space between two such adjacent lane divisions. To model this idea, we recognize that any two instances in our table paired together yields an instance of another class. It's shown on our model as a lane class, which is instantiated by the inside-outside adjacency relationship. Notice that the lane table has 3 columns instead of 4. That's because each lane division must be part of the same road segment, and therefore we can share the road segment column in the new table. We can now populate this table to represent the entire lane structure of our road segment's forward conduit. But wait a minute, how do we detect those lane divisions? Our models don't really specify how detection is performed, but they do specify that lane divisions must be detected. Presumably some combination of machine learning, sensor fusion, and mathematical curve fitting may be employed to establish the divisions. In fact, the models of our driving environment domain help identify and define requirements to be imposed on other models or software in supporting domains. For example, in addition to the requirement of detecting lane divisions, our complete model also requires differentiation between physically non-traversable barriers and soft divisions such as paint that can be traversed. The value of a model is not just in what it captures, but what we decide to leave out. For any model to be useful, it must systematically exclude certain kinds of details while focusing a bright spotlight on others. In the driving environment models, we purposely exclude sign, signal, and symbolic interpretation. For example, we model a lane division without regard for whether or not it is signaled by a painted stripe. It gives us a nice case for why this distinction between signs and semantics matters. So how is a lane division different than a painted stripe? A lane division, as we've abstracted it in the model, is a true one-dimensional line with a position relative to its road segment. Lane divisions aren't much use to us if we don't know where they are. We also care whether or not the division is hard or soft. Can we physically drive over it? Assuming it is soft, are we allowed to cross it? Are we allowed to pass oncoming traffic? So we focus on meaning, not representation, when we describe a lane division. We also care whether or not this lane division is temporarily overriding some previous lane division. A line of cones or special paint might indicate a temporary diversion, for example. By contrast, a painted stripe has a visual representation consisting of a color, dash pattern, and width. In fact, paint has a great deal of regional variation. The way streets are painted in one country or region can appear wildly different, even within the same country, but especially between countries. Regardless of the painting scheme, we need to detect the lanes and their policies, irrespective of how they are indicated. I can't tell you how many times that I've looked at a street view in some other country and felt like, oh my God, this is so complex, we'll never be able to model roads. But then I take a breath and realize that I'm just being dazzled by the paint patterns, and as soon as I look through all of that and perceive the underlying lane divisions, I realize that there's really nothing new going on. To further highlight the sign versus semantics distinction, note that a painted stripe is just one of many ways to signal a lane division. The two divisions bounding this dedicated bicycle lane, for example, are indicated by a color contrast. Our model doesn't care about the color or pattern, but it will model facts such as the policy that it's not okay to cross into the bike lane whenever you want, and that it's a permanent division, though it is physically traversable. Next, we see a linear pattern of cones manifesting a temporary lane division. I expect we could argue the point as to whether or not it's physically traversable. We certainly aren't allowed to cross it, and it is temporary in that it overrides any nearby permanent lane marker. But what about snow and ice, which obscures the entire road surface? In a situation like this, we may ignore both paint and map information and instead use contrasting visual and other sense data to identify both the road edges and also to use the rut boundaries to establish temporary lane divisions. Similarly, curb and median edges may serve as unpainted lane divisions. And don't forget lines of dots and reflectors. Now, just because we exclude certain kinds of details from our model doesn't mean that they are unimportant. To the contrary, these details are so important that they constitute one or more domains, each with its own distinct vocabulary, that can be modeled or coded. In fact, the vehicle environment domain establishes requirements for any domains that it relies upon. For example, one or more domains are required that determine region-specific policies indicated by lane division markings, detect linear cone patterns, detect temporary stripe markings, detect longitudinal linear contrast on a weathered road surface, and so on. That's probably enough for now about our modeling assumptions, which we will come back and review from time to time. For now, let's get back to modeling lanes. Our goal is to define some useful and stable lane categories to account for the wide variety of lane usage possibilities. And in our next video, we will do just that.